For the last unit of the year, we are going to study an entire unit about the properties and theorems about circles. So every single picture you're going to look at is going to involve circles. So the first part of this is a little bit of vocabulary. So a couple of things about a circle. Number one, by definition, a circle is just a grouping of points that are all the same distance from a center point. So all of these points all the way around your circle, all the way around, all of those points that I'm outlining here in black, every single one of those points is the exact same distance from a center point called the center of a circle. The distance from that center to the edge or to those points is called the radius. If you connect one side of the circle to the other side through the center, it's called the diameter. Those are both vocabulary terms that we're familiar with. The newest vocabulary term here is this concept of a chord. A chord also attaches two sides of a circle, but it does not have to go through the center. So a radius from center to the edge, diameter edge to edge through the center, and then a chord is edge to edge but does not have to go through the center. Two more vocabulary terms. We've got this line called a secant. A secant line is a line that touches two edges of the circle. However, it passes through the circle. So the difference between a secant and a chord is that a secant is a line that does not have end and touches the circle twice. A chord is a line segment, so it has endpoints that are on the edge of the circle. Secant is a line, chord is a line segment. The other two new terms here are a tangent and a point of tangency. A secant line touches your circle twice, that's outlined there in purple. A tangent line is a line that touches a circle exactly once. Where that line touches the circle, that's called your point of tangency. So a tangent line touches a circle one place, point of tangency. A secant line touches a circle twice. A chord is a line segment with endpoints on the circle. Radius goes from center to the edge. Diameter goes edge to edge, but goes through the center. So several different vocabulary terms that your book is going to throw out, so you just need to be familiar with what they mean and what they would look like visually. Moving down here, we've got a picture on the right-hand side, and what we're going to do is we're going to identify if AC here is a tangent, a radius, a chord, a secant, or a diameter. So AC is this blue highlighted segment. It goes from center to edge, so it would be called a radius. The next one we're going to talk about here is a chord. AB, is AB. We're going to determine if it's a chord. AB goes edge to edge for the circle, and it passes through the center, so it is called a diameter. The next one we're going to worry about here is DE. DE starts here and goes down. Notice that it touches the circle one place, and that's at B. That's called a tangent. And then the last one is AE. AE would be here, the line that connects A and E. Since it hits the circle twice, it would be called a secant. Secant hits twice, tangent hits once. If we were to, this one's not on here, but if I added an extra one, letter E, what if I asked you about line segment AG? Notice I have line segment listed, not line. Since it's line segment, that means it has these two endpoints at A and G. Since it's a segment, it would actually be called a chord. If I changed it and asked you about line AG, where it would continue through AG, we would actually have a secant, not a chord. That's the difference between a secant line and a chord. A secant is a line without end, and a chord is a line segment with endpoints on the circle. It's kind of a little bit of touchy vocabulary, kind of technicality, but it is the way it is. So moving down, a couple of different properties about tangent lines. Number one, anytime you draw a tangent line on a picture, if you connect the radius to the tangent line, they are always perpendicular. So a radius and a tangent line are always perpendicular. So let's talk about number two first, letters A and B. Let's look over here first. So the first thing is, notice I've got a tangent line and I've got a radius. Notice how we've labeled it with a right angle here. So what I have is a right triangle. And if I want to figure out the length of x, anytime I have a right triangle, all I have to do is use Pythagorean theorem. So if I use Pythagorean theorem, using a calculator, we are going to figure out, well, what's 80 squared and what's 48 squared? 80 squared is going to be 6,400. 48 squared, 2304. So to solve for x, we're going to have to first subtract. We get 4096. And then the last thing we would do is take the square root. And we get an answer of 64. So that means that that length in your picture from A to B has a length of 64. And it's just all using Pythagorean theorem. In the next one, again, we've got a tangent line and a radius. There should be a right angle there. I should have put that in. So what we've got here, again, is a right triangle where we can use Pythagorean theorem. Now, here's the deal with this one. My legs are r and 80, so r plus 80 squared. My hypotenuse, however, is not just 50, and it's not just r. It's actually r plus 50. So I have to take r and 50 and add them together and square that result. So on the left-hand side, we have r squared plus 6,400. The right-hand side is a little more complicated than that. So what we're going to need to do is recall a little bit of algebra rules. So I'm going to rewrite this on this slide so that we can figure out what that right-hand side is going to look like. Now, anytime you have something squared, remember from Algebra 1, that means that you have that parenthesis written 2 times. Now, as soon as I write this, I think you're probably thinking in your head, okay, I remember that. I would use FOIL to do it. First, outer, inner, last. Okay, so you're going to FOIL this. So the first thing we're going to do is multiply the first terms. R times r is r squared. Then we're going to multiply the outer terms. R times 50 is 50r. Then we're going to multiply the inner terms. 50 times r is 50r. And then we're going to multiply the last terms. And so 50 times 50 is 2,500. So if I simplify that, I can add my middle 2 terms together. We get r squared plus 100r plus 2,500. So what we're going to do is take that, what I just got, and we're going to write that on the right-hand side of the equation that we're trying to solve. So we would have an r squared plus 100r plus 2,500. Now it looks a little complicated, but if you'll notice what happens to the r squareds, there's 1 on each side, so they're actually just going to cancel out. If I want to solve for r, I would have an equation that says 6,400 equals 100r plus 2,500. So the r squareds are gone, so now it's just a pretty simple equation. So let me move some of this down first. Give myself a little bit more room. So to solve for r over here, we're just going to continue with our algebra rules. We would subtract 2,500 from both sides. Doing that is going to give me 3,900 equals 100r. And then the last thing I would do is just divide by 100. So I get an r value of 39. So what started out pretty complicated actually ended up not being so bad as long as you do your algebra correct. So let's come back to number 2. Number 2, we're supposed to prove or show is TS tangent to circle P. So the way that we need to show that is we have to ask ourselves, does that tangent line hit at a right angle with TP, which is a radius? Now, because it looks like it is not an acceptable answer. What we need to show is that a right angle? We don't know. So what we need to do is figure out whether it is a right angle. So I need to figure out, is this triangle STP a right triangle? Okay, that's the question I'm asking. Because if it's a right triangle, then that means that ST and TP are in fact perpendicular, which means that TS would be a tangent line. So if to figure out, we're going to use the converse of Pythagorean theorem. This is something we learned about earlier this year. So we're going to take the longest side, which is 37. We're going to square it by itself. We're going to take the shorter sides, 12 and 35, and we're going to square them together. If each of those columns comes out the exact same number, then we know that we have a right triangle. 37 squared comes out 1369. If I do 12 squared, I get 144. If I do 35 squared, we get 1225. Adding those together gives me 1369. So since the two columns came out the same, that means that we do have a right triangle. And so in fact, that is a right angle. Since that's a right angle, that means that TS is tangent to circle P. And there's your explanation on why. Yes, it's a tangent because I was able to show that triangle STP is a right triangle, which means that the tangent and the radius are perpendicular. Coming down, what we find out, another property of tangents, is that if I have two tangent segments that are segments to the same circle, then that means that they're congruent if they meet outside the circle. So anytime I draw a tangent line from R out to S and T out to S, if they're both tangent to the circle and they both meet at S, that means that the two blue segments are congruent to each other. So from R to S would be congruent from T to S. So in every single one of these pictures, all we're going to do is notice that each one of these is a tangent. They all meet at the same letter point outside the circle. So all I have to do is say that those two segments are in fact equal to each other. Very easy equation to solve at that point. All we're going to do is subtract 4 to get 24. And we're going to divide by 3 to get a value of 8. The next one is really no different. They're both tangent to the circle. They both meet at J, which means the two blue segments here are in fact equal to each other. Now you might be looking at this equation like, well, that's not so easy to solve. Well, let's see that it actually is pretty easy to solve. Number 1, to get x by itself, I first would need to add 10. So I would get 27. In order to get the x by itself, the next thing we would need to do is divide by 3. Don't ever take a square root until you get the x squared completely by itself. Now in explaining that step, I just gave away what we're going to do in the next step, which is to take the square root of both sides. And we will get an x value then of 3. In the last one, these again are common tangents. They both meet the same circle at a single point, and they meet the same point outside the circle. So we know that those two segments are in fact equal to each other. Now this one may not be so easy for you to solve. What we're going to do here is notice that this is a quadratic equation. in order to solve a quadratic equation, we need to get it equal to 0. So the first thing I'm going to do is subtract 3 from both sides. And we get 2x squared plus 3x minus 5. This is something you learned how to solve last year in Algebra 1. And you learned how to solve it using something called quadratic formula. Quadratic formula looks like this. So what we need to understand is the number in front of x squared is the a, the number in front of x is the b, and the number here on the end is the c. So it's just a matter of plugging those numbers into the correct places. So opposite of b would be a negative 3, since above b is positive 3. Under the square root, we'd have a 3 squared minus 4 times ac. So 4 times 2 times negative 5. And then all over 2 times a, 2 times 2. Now, you may not feel comfortable simplifying this by hand, even though I know you learned how to simplify it by hand in Algebra 1. So all you need to do is type this in the calculator, and it's going to end up giving you the right answer. So just very carefully, we're going to type this in the calculator. And typing it in the calculator is going to give you two answers. One of them is positive 1, and one of them is negative 2.5. Now, since we're dealing with geometry, we're only going to accept the positive answer. So we would say that our answer is positive 1. If you need help on how to type this in the calculator correctly, we can talk about that in class. On the back, we're going to talk about a couple of other concepts, and they would be central angles and arc measures. So a central angle is very, very easy concept to understand. It's an angle that has a vertex at the center of the circle. So the angle I just highlighted in purple, angle APB, that is a central angle because its vertex is at the center. The angle that I highlighted in blue, angle CPB, that is a central angle because it has a vertex on the center. We also have these two things called major and minor arcs. A minor arc is formed when your central angle is less than 180, so it is a small arc. So we would say that from C to B is a minor arc because it's a small arc less than half of a circle. So CB would be shown with this notation, CB, and then it has an arc over the top, showing that it's an arc. You could also name that arc BC with an arc over the top. Either one of those would name this arc that I highlighted here in this grayish color. A major arc is one that is more than 180 degrees. So if I started at A and went all the way around to B, that would be a major arc because it's more than 180 degrees. It's more than half of a circle. So there are two ways I could name this arc. We could start at A, go to C, go to B, and put an arc over the top. Or I could start at B, go to C, go to A with an arc over the top. Notice where I started and where I ended are always the first and last letters. The letter that we pass through on the way between is always the center letter. And again, arcs are always named with that arc over the top. The last thing is a semicircle. A semicircle is just half of a circle. So I have a couple of semicircles on my picture here. From A around to C this way is a semicircle, and from A around to C this way would be a semicircle. So we're going to come down here, and all we're going to do is determine whether the arcs are major or minor. AE starts at A and moves to E. So anytime an arc is named with two letters, you're going to go the shortest distance from A to E. So we would go down to the right through D because A through FB would be the longer path. So two letters is always the shorter path, so this is going to be a minor arc. FA, again, shortest distance since it's a two-letter arc, and this would also be a minor arc. If I do AEB, start at A, go to E, down to B, since we've moved half of a circle, this is a semicircle. BE, I start at B, shortest distance to E, that's a small arc, so it is a minor arc. FDE, start at F, go to D, go to E, so that again is half of a circle, so that is a semicircle. BDA, we'll start at B, go to D, go to A, again half of a circle, so that's a semicircle. Okay, let's do DFB, starting at D, going around to F, and then finishing at B. So DFB, notice this is more than a half rotation, so that's going to be called a major arc. And then the last one is FB. FB, again, is going to be the shortest distance because it only has two letters, so that is going to be a minor arc. Coming down, arc length, or arcs have two different kinds of measurements. They have a degree measure and they have this thing called arc length. So here we're just going to talk about their degree measure. So all we need to know is that the measure of an arc out here is always the same degree measure as its central angle. So since the central angle GHF is 60, that means that the arc measure for GF is 60. Arcs and their central angles always have the same degree measure. So coming down, what I would do is I would actually figure out what's missing in the picture before I even worry about all of these measurements. So the first thing I would notice is, since NR is a diameter, that means that these three angles have to add up to be 180. So I would take and figure out what the middle one is here by just subtracting from 180 first. So if I subtract 82 and 63, I get a measurement of 35 degrees, and that's then going to help me figure out the other ones that are missing. Since this is a diameter, these have to add up to 180. So if I take 180 and take away 63, this one here is 117. And again, since this is a diameter, these have to add up to 180, which means that this one is also 63. So knowing that all of these arcs here, this one here is 117, this one is 63 degrees, 82 degrees, 35 degrees, and 63 degrees, all of the problems here now all just become simple addition as long as you know which arc you're looking for. So I'm going to erase all this stuff in the center because we've now labeled all the arcs, and now it's all addition. So if I want to know, for example, QMR, I'm going to start at Q, go around, oops, wrong way. Start at Q, go around to M, finish at R. So I've done almost a full circle. So I can figure out what that arc measure is by doing one of two things. I can either add up the 4 arcs around that I touched, or I can see that I'm only missing one of them and subtract 63 from 360. So I'm just going to add them all together. So I've got an arc of 35, 82, 63, and 117. So by simply just doing addition, we get a total of 297 degrees. Just one more for an example, and then we'll be done. So if I do an arc like this one, PRN, if we start at P, the first letter we go to is R, and then all the way around to N. So again, that's a major arc, and I've touched 1, 2, 3, 4 different arcs. So to find that measurement, all I'm going to do is add up the arcs that I've touched. So we're going to let's see, we touched 35, we touched 63, 117, and 63. So by simply adding all of those numbers together, we're going to come up with the measure of that arc. And we get 278. And arc measures are always in degrees. So if you would please just finish up the rest of the ones that we didn't do right there, so that when Mrs. McGee comes around to check your paper, you have all of the rest of them filled out. And again, it's just simple addition, so go ahead and do that on your own. If you have questions, make note of what they are so that you can ask in class.